Okay, what we're going to look at, ladies and gentlemen, is a demonstration here on some Calculus 1 concepts as it relates to some additional functions, these inverse trig functions. So the first question we're going to look at is intervals of increasing and decreasing, and if there's any relative max, relative min values. So questions 1 and 2 here for the inverse trig function of inverse tangent. Now, what I sent you guys here is a derivative and integral formula sheet. And we're going to look at here the tools we need, derivative of inverse tangent, and it's actually going to be chain rule here. So we're going to look at the chain rule for the derivative of inverse tangent, and it's going to be 1 over 1 plus u squared times du dx. Chain rule. Okay. So let's see about possibly getting pages here. We're going to keep adding some pages. And for these pages, we're going to make line paper. Okay. And there we go. Okay. Now let's remember what that was. That was going to be x minus 1 over x plus 1. Okay. We're going to let this whole portion here be our u now. Okay, so we're going to have to use chain rule. So the derivative here of inverse tangent, and you can think of that as your u now. This is the u we're talking about. That's going to give us 1 over 1 plus u squared times du dx. This is the chain rule version, which is really 1 over 1 plus x minus 1 over x plus 1 squared times the derivative of x minus 1 over x plus 1. So here's the u, and that's du dx. Now, this is the portion here on this side we're going to have to use quotient rule. So by quotient rule, we have x plus 1 squared, x plus 1, d dx, x minus 1 times x minus 1, d dx, x plus 1. This derivative here is 1. These are these derivatives here. And I get x plus 1 times 1 minus x minus 1 times 1 over x plus 1 squared. So we're going to distribute here. And sure enough, we're going to get 2 over this x plus 1 squared. So we're going to double check to see if we did everything okay. So this is going to be this portion here. 2 over, say, x plus 1 squared, I believe. Yes. Now, all together here, we're going to have another part that we're going to have to do some algebra for. Okay, so let's take a look at the algebra we do here. One over 1 plus x minus 1 squared over x plus 1 squared times 2 over x minus 1 squared. So down in here, we're going to do some arithmetic here. This is a complex fraction. I'm going to write this as x plus 1 squared over x plus 1 squared. So in this denominator portion, you get x plus 1 squared over x plus 1 squared. And don't forget 2 over x plus 1 squared. So we're now going to be able to add these fractions here in the bottom here, the denominator. And you'll have x plus 1 squared plus x minus 1 squared over x plus 1 squared times 2 over the x plus 1 squared. So let's look at this as a complex fraction here, because that's what this is. This is 1 divided by x plus 1 squared plus x minus 1 squared over x plus 1 squared times 2 over x plus 1 squared, which is going to give you 1 times that reciprocal. Okay, and so you have this x plus 1 squared over x plus 1 squared times x minus 1 squared times 2 over x plus 1 squared. So you get to cancel this. So you get 1 divided by that fraction here. If you wanted to put this in a bracket, just flips this over and it looks like we get some nice cancellation. And so what we have here is our derivative becomes 2 over x plus 1 squared times x minus 1 squared. And when it looks like we're not done here, we're going to have to do a little bit more algebra here. You're going to have to distribute. X squared plus 2x plus 1 plus x squared minus 2x plus 1. And this is FOIL for each. So we have 2 over 2x squared plus 2. And it looks like we'll have 2 over x squared plus 1. And we can cancel the 2's. So it looks like we have 1 over x squared plus 1. And this is the first derivative here. So with all that work, we should probably have an applause here for that, right? All right. Now remember, whenever you have this kind of question of intervals of increasing, decreasing, right? If you remember what I mentioned in class, intervals of increasing, decreasing, what that's code for doing is sign analysis on the first derivative. Okay, sign analysis on the first derivative. So here's our first derivative. We got to do sign analysis. Okay. And so we're going to look for critical values. So if you were to try to say, for example, how do you go about finding critical values here? Well, you want to find where the first derivative is 0. remember, and find where the first derivative does not exist, or it's not differentiable. So when you say y prime is 0, that's saying 1 over x squared plus 1 equals 0, which is really saying that 1 equals 0, and that's a false statement. So this never happens. This is a false statement. So in other words, that first derivative is never equal to 0. Essentially, your numerator, you're trying to set the numerator equal to 0, which you have here, and that doesn't happen. It could never be 0. You're saying 1 is 0, and that's not true. And then when you look at the denominator, you're trying to find where this derivative does not exist. And if we set the denominator equal to 0, we say, hey, x squared plus 1 equals 0. This also never happens as well. This could never happen. You know, because if you try to do some algebra, you'll say x squared is negative 1. You start getting complex numbers. So this doesn't happen either. So this is setting the denominator equal to 0. And I'm looking at the colors here, and my colors don't match. So I'll make sure they do. This is essentially attempting to do sign analysis. Now, as you can see here, there's no critical values for this derivative. Okay? So we have no critical values. And we want to know what this means then, right? Since the first derivative, let's take a closer look. First derivative is 1 over x squared plus 1. So what this means is you give me any test point, and it doesn't matter what the test point is. I'm going to use a 0 here. If I plug in 0 here, notice I get a positive answer, meaning that first derivative will be 1 over 0 squared plus 1. That answer is 1, but it's positive. So here's what this means. Okay, you have simply an increasing slope on the first derivative, because this is sign analysis on that first derivative. That means the first derivative is always positive for all your x values. Now go back and you say, what do you mean all the x values? This function here, right? This is a function that's inverse tangent. The inverse tangent function of, let's write down what this function is. Y is inverse tangent of, I believe it was x minus 1 over x plus 1. All right. Now, let's note something here. X could not be negative 1. Or can it be, right? So I want to take a look here. I want you guys to take a look at this in Desmos here. So we're going to get rid of some of these things. So here's what I'm saying. You have y equals, here's your function, inverse tangent. And that's x minus 1. And I think I'm going to go back here with 2 parentheses. Okay. And so take a look at what's going on here around negative 1. The function's not defined at negative 1 because you can never divide by 0 here. And when you took the first derivative, what you're supposed to be saying is an increasing slope for all real numbers. Okay. So if I go back here, and let's notice this. To say your function here, with that derivative always being positive, it is for all x, but x can't be negative 1. It's not in the domain. So here's our conclusion. That the function f, this particular function, is increasing for all real numbers x, with the exception of being negative 1. So this is going to be from negative infinity up to negative 1, union negative 1 to infinity. Because the function is really not defined at, negative 1. And so we should have done sign analysis in that way. We should have said we got to throw out negative 1 here, right? So negative 1, this is not defined. The function's not defined. Anyway, we just want to go back to see what that domain was. So this is all positive for all real numbers except for the value of x being negative 1. This is not in your domain here. So your function's increasing on that interval, and f is simply not decreasing anywhere. And notice you don't change your increasing, decreasing. There's no change. At negative 1, you're not defined. There's a hole there. Okay, and so there's also no relative max, no relative min. You don't change your increasing, decreasing. There's no hills and valleys. Okay, there's no hills and valleys here. What comes next? They ask us in this situation here. What comes next here? After trying to address the relative max, relative min situation is the intervals of concavity. So when you try to do intervals of concavity now, this portion here, sign analysis. On the second derivative. So once you get the first derivative, you're going to have to now get the second derivative here. Okay, so the first derivative is right here. So let's do sign analysis on the second derivative. Now, y double prime here, if we say let's find what y double prime is. The second derivative here is the derivative on the first derivative. So you can use quotient rule again. Okay, here's quotient rule. Call that QR. X squared plus 1 times 0 minus 1 times 2x. Everything over x squared plus 1 squared. So the second derivative is simply going to be negative 2x, x squared plus 1 squared. And remember, what's not in the domain of the function is negative 1. So when you do sign analysis this time, again, I'm going to set that numerator equal to 0. You can keep the negative sign there. Set the denominator equal to 0, your sign analysis. So you got negative 2x equal to 0, which really means x is 0. It's not a critical value. X squared plus 1 squared is 0. Again, implies x squared plus 1 is 0, and that never happens. Okay. So this does not add to the sine analysis. Never happens. So here's what's going on again. Yes, you have 0. The second derivative at 0 is 0. You can throw out the point -1. It's not there. So we have region 1. We have region 2. -1 is not in my domain. So we have 2 regions now. I'm going to use 1 as a test point, and then I'm going to use maybe -2 as a test point here. So we're going to test region 1, region 2 with these test points and that second derivative right here. All right. So for region 1, let's try -2 there. Plug in a -2. Y double prime will be -2 times -2 over, that's going to be 4 plus 1, that's 5 squared, that's 25. And negative times negative is positive. So region 1 is positive. We're going to plug in 1 now for a test point. And you're going to get a negative value. So that second derivative is negative. So it looks like it'd be -2 over 4. The point is, it's actually negative. So we have concave up, and we have concave down. Okay, there's a point in which we change our concavity, though. That happens at the x value being 0 here. So let's actually summarize what this information means, the sine analysis on the second derivative. Here's what this means. The function is concave up, where the second derivative is positive. Now remember a few things here. At -1, the function's not even defined. So what I'm going to say here, this is from -infinity up to -1, union -1 up to 0. And this is supposed to be a union here, because this is the interval in which you have second derivative being positive, concave up to 0. And then from 0 to infinity, it's concave down. So f is concave down on 0 to infinity. You do have an inflection point when x equals 0, but what's the y value? You have inverse tangent 0, I believe, -1 over 0 plus 1. And you have y equals inverse tangent at -1 here. Okay, because we're going to have to look back at that function. That function is going to be right in here. Let's copy it down. So this is what we just did. We plugged in the value for x here, x being 0. This is how we have inverse tangent -1. Now, you have to answer the question, what is the inverse tangent of -1? What's that angle, right? So you can think of it as, we can say, let theta be inverse tangent -1, which means tangent theta is -1. Okay. Sorry, let me get this out. Sorry, let me get some things here. Okay. And so remember this tangent function if it's going to be invertible. I want to try to remember when this is. So essentially this is pi over 2 minus pi over 2. The reason I'm saying this is because if you remember, this is quadrant 1. And this will be quadrant really 4. Quadrant 1, quadrant 4. Because if you tell me theta is going to be negative pi over 4, that's going to be the correct answer because that's a quadrant 4 angle. This is the green color, quadrant 4. So that's really what the y value is. In other words, you have an inflection point at 0, negative pi over 4. This is what we were looking for. So we have information about concavity. Concave up on the interval from negative infinity up to negative 1. Negative 1 to 0. Concave down in 0 to infinity. Inflection point at 0, negative pi over 4. And if we looked at Desmos, essentially that's kind of what's happening there. They're saying you have an inflection point here at 0, negative pi over 4. Okay, you're going to be from negative 1 up until that point 0, it's concave up, and then you're going to have concave down from, looks like 0 to infinity there. So this is the curve. And again, now we want the limits here at infinity here for this curve. So if you said, okay, what about limits at infinity? Remember, the curve is going to be x minus 1 over x plus 1. So limits at infinity now. This is going to be the last portion of what they ask us here. Let's go back to the question. Limits at infinity. Okay. As x goes to infinity, the question is, what happens here with this? Okay, you can do a substitution, I guess. We could let this be t, right? So let t be x minus 1 over x plus 4. So you're going to now get this limit as x goes to infinity. What happens to this t? This is t right in here. Right? This is the t variable. Now, this is a calculus 1 question because you could divide everything by the highest power in the denominator, the highest variable, and that's just going to be an x. So we divide everything by x, if you guys remember that. And so you have the limit, x goes to infinity, 1 minus 1 over x, 1 plus 4 over x. So as x gets big, t here goes to 1. Okay? So t goes to 1, and this is as x goes to infinity. All right. So we need to know what the inverse tangent. Now, where does that inverse tangent of t go to? Right? Because that's going to 1. So you're going to need the curve for the inverse tangent here. Pi over 2 minus pi over 2. This is the curve. I guess this is t here. Well, this is a nice continuous curve. Okay, this curve is nice and continuous here. So this goes to, if t is going to 1, inverse tangent of 1, we have to know what the inverse tangent of 1 here is. And that's going to be pi over 4. So this goes to pi over 4, because that's the value of inverse tangent of 1 here. All right, so this is the first limit. Limit as x goes to positive infinity, so this would be pi over 4. Now we look at this limit. As x goes to minus infinity, t goes to same kind of place. So if we looked at that limit, that's also going to be 1 again. So t goes to 1, which means inverse tangent of t goes to inverse tangent of 1, which is also pi over 4. So this goes to pi over 4 as well. So it looks like we have these, what are these called here? Horizontal asymptotes at y equals pi over 4 here. So anyway, this is why we looked at those limits. I guess we have to color it in black, maybe. Anyway, limits at infinity. You have horizontal asymptotes at y equals pi over 4. And that's what the limits at infinity give you. So let's verify that with the graph in Desmos here. So I'm going to put here y equals pi over 4. And I want that to be dotted. So here's what I'm saying here. Here's the line y equals pi over 4. And as you guys can see, if it goes to the left here, that curve approaches this horizontal asymptote of pi over 4, and that's what I'm illustrating. And as you go to the right here, as x goes to positive infinity, you still go to pi over 4 here. So sure enough, yes, this is the essence of the curve here that we're looking at with Calculus 1 techniques here. Okay. And that ends our demonstration. So what I'm going to say to you guys here is take a look at the other questions here that I have for you to do, and you do the same kind of thing with these functions. Find the intervals of increasing, decreasing, relative max, relative min, if any. Intervals of concavity. Also should put comma inflection points, So I should fix that to some degree. And you have some other functions you could take a look at. So I want to clear this up. So this is a demonstration of really some Calculus 1 techniques as it applies to the inverse trigonometric functions. I hope you guys remember those kind of things anyway. Thank you for watching this demonstration. Okay, good morning. We're going to work on some Calculus 1, applications, or I should say concepts, with inverse trigonometric functions here. So these are things that you studied, all of these ideas you studied in Calculus 1, intervals of increasing and decreasing, relative max, relative min, intervals of concavity and limits at infinity. So we're going to take a look at this first function here. And we're going to review these items, these concepts, with these new functions here. I don't think I'm going to do all of them at all. I think I'm going to do one, maybe two. We'll see how this goes. But I want you guys to review these concepts so that you're ready to apply them as well. So the first function is inverse sine x over x plus 1. Okay, now here's what we can do. So here's our curve. It's inverse sine x over x plus 1. Now, when they ask you for intervals of increasing, decreasing, okay, this is code for sine analysis on the first derivative. Okay, so intervals of increasing, decreasing for a function is sine analysis on the first derivative. And you're going to need to know the derivative of the inverse sine function. Okay, so I also submitted to you guys here, what do we have it called? The formulas. And for inverse trig functions, this was actually the first formula that, in class I derived for you guys. So that derivative formula is going to be 1 over the square root of 1 minus x squared. Now remember, this is only good for -1 to 1. That derivative, anyway. Okay. So let's differentiate this. Y prime, using that derivative formula, 1 over the square root of, now remember with that formula here, even though we have that derivative, we're really using the chain rule version here of that derivative. Okay, so this is going to be what we use. Don't forget, this is one of the most important parts, where if you have here, for example, this is my u goes here. But this is the chain portion. We need to differentiate u with respect to x. So don't forget your chain portion as well. This is the derivative here for inverse sine of, u, which is a composition of functions here. So you might say, how does that work with us here? Well, this is that u. So we're going to take this portion here, this u portion, and of course we square it. And this is the chain portion in chain rule. So here is that u. And, you don't have to write it down that way, but you don't have to notate it. But here's the point. So this portion here, this is the chain rule. And that's the part you don't want to forget. Yeah, you never want to forget that chain portion. What else did I want to say here for you guys on that? This is where the work is going to be. Because we have to differentiate now x over x plus 1. And this is what we're going to use here to do that. Remember, you're looking at a quotient. So you're going to have to use quotient rule here. So I'll put this portion in purple, quotient rule. Remember, you take the denominator and you square it. Bring your denominator x plus 1 up, and then you differentiate that numerator. And there's x d dx x plus 1. Now, this derivative is 1. This derivative is 1. So you'll have x plus 1 times 1 minus x times 1. And this would be over x plus 1 squared. Okay. x plus 1 minus x over x plus 1 squared. And that's going to be simply 1 over x plus 1 squared. So this is the portion that we get when we differentiate the chain portion. Okay, so let's not forget that we're going to have to bring the rest of this down, and we're going to have to do some simplification here. So we're going to copy that down. We're going to bring this down here. There you go. So here's where we're going to have to do some work. Right, we're going to have to simplify this portion down here. And I'm talking under this radical. So I'm gonna do some work here, some algebra down here. Okay. Right, this portion. So remember, that's going to be 1 minus x squared over x plus 1 squared. So you're really subtracting here rationals, but remember, you need to have the same denominator if you're going to subtract. So we're going to put that denominator down here of x plus 1 squared. Okay, you need this denominator. So this gives us x plus 1 squared now over x plus 1 squared minus the x squared over x plus 1 squared. Now we have x plus 1 squared minus x squared over x plus 1 squared. So this portion, I'm going to say to you, would need to be simplified here, meaning on top we're going to have to use FOIL. So x plus 1 times x plus 1 minus x squared over x plus 1 squared. So by FOIL, you get x squared plus 2x plus 1 minus x squared over the x squared plus 1. And then you end up with 2x plus 1 over x plus 1 squared. And that is under the radical here. So in other words, let's double check. Yeah. All right. So y prime is 1 over the square root two x plus 1 over x plus 1 squared times the 1 over x plus 1 squared here. So we did the work here in gray. Okay, all of this is in gray. So this is 1 over x plus 1 squared. So okay. Now we are not done here with simplifying. I want you guys to really pay a close attention to this portion here, because this is kind of like, not kind of, this is exactly like saying you have 1 divided by 2x plus 1 over x plus 1 squared, which is 1 times the reciprocal of that fraction, x plus 1 squared over 2x plus 1, which is simply going to be x plus 1 squared over 2x plus 1. Now that numerator, if I said to you, this is x plus 1 squared over the square root of that 2x plus 1. And then this is times, don't forget, you're going to have that. Well, we can actually still continue with this simplification here. You get x plus 1 over the square root of 2x plus 1. So this is the portion here that can be simplified further, and then you still have the chain rule portion, that factor of 1 over x plus 1 squared here. So altogether, here's what you're going to get. Y prime x plus 1 square root 2x plus 1 times 1 over x plus 1 squared here. Let's double check. Yes. And then you may notice a factor of x plus 1 goes away. And you're finally left here with y prime going to be 1 over the square root. And I actually feel better if I write the x plus 1 first. 2x plus 1 here. Okay, and there you go. So here's my first derivative. Now let's remember a few things here. The inverse sine function, if I ask you this question here, what's the domain here? Right? What is in the domain of this function? Inverse sine, the inverse sine here is defined for what values of x, if you remember that, what input values? When you had the definition of inverse sine here, we wanted to remember what the inputs were good for. Okay? The input values were good for -1 less than x less than +1. Now, the problem here is that x plus 1, the denominator down here, x cannot be -1. So what you're going to have here for your domain is -1 will be less than x less than or equal to +1. Okay? And let's double check. All right. So I'm going to copy that here. And of course, when you differentiate this, you say, well, the derivative here is only good for -1 to +1. So you get to throw out that value as well. But anyway, okay, here's my domain here. And we have to do sign analysis on this. So let's find the critical values. We're going to go through the procedure for sign analysis. Now remember, in the procedure for sign analysis on a first derivative, the numerator gets set equal to 0, and the denominator gets set equal to 0. So that's equivalent to saying, where is the derivative equal to 0, or where is that derivative does not exist? And if you try to set that derivative equal to 0, you simply know that you're saying 1 is 0, and that's simply not true because that's the numerator, right? So that's kind of implying here, you're trying to say that 1 equals 0, and that's not happening. So that never happens. In other words, the derivative is never 0. Right? Because remember, when you try to set a fraction equal to 0, that simply implies that numerator is 0, and that's not true. So this derivative could never be 0. But what about if the derivative does not exist? X plus 1 square root 2x plus 1 is 0. So where in the world does this happen? Well, you got x plus 1 equal to 0, which means x is -1. And then you got the square root of 2x plus 1 equal to 0, which means 2x plus 1 is 0. Or 2x is -1. And we get x is equal to -1/2. And that never happens as well. I apologize. X is -1/2. This is my solution here. So let's go back and remember here. What's the story with this particular situation? What does this mean here? You got x is -1, and we have to throw that value out because x can't be -1. It's not even in the domain of the function. Okay? It's not even in the domain we go back to look at the domain of this function, we can't have negative 1, right? Because you'll get this here, this fraction will be undefined. So you can't even have negative 1. So what you'll have to do here, ladies and gentlemen, is notice that you have one critical value. X can be negative 1/2. So here's my critical value. Okay. All right. So trying to find sign analysis here. Here's 0 here. Here's negative 1/2. Typically, we know the derivative is going to be undefined here. So typically, when we do sign analysis on that first derivative here, this derivative right here, we really have two regions here. So we need a test point, right? And we're going to have to remember here that we're going to go all the way up to negative 1 here. I mean, we can't have a, region 1 is technically from negative 1, don't include negative 1, up to negative 1/2. So it's going to help us find this particular test point. That's going to be negative 3/4, I guess. So here's our test point. And then you say, well, what about, what are we going to have here on the other side? Well, I'm going to remind you guys here, I'm going to choose maybe a positive 1/2. Okay, this would be my test point. Yeah, or I can choose, positive 1, whatever is easier. So we're going to test these regions here. So we want to find the sign of that first derivative. If I plug in as a test point, negative 3/4. Negative 3/4 plus 1 here. So this would be 1 over negative 3/4 plus 1 is really 1 minus 3/4. So that'll be 1/4 times the square root of 2. So that's negative 6/4, or we should say negative 3/2 plus 1. That's the square root of 1/2. The point I make is this is going to be positive. Okay, so in region 1, we have an increasing slope. Region 2, you know what I'm going to do instead? I'm going to use the test point of 0. I think that makes everything a lot easier. Notice this. So I apologize. I'm going to use these two as a test point. 0 is available. So if I plug in 0 now, that'll make everything nice again. So 0 plus 1. So this would be 1, square root of 1. This is positive. And so, ladies and gentlemen, we're going to have to take a look and try to describe the meaning of this, right? Okay, I'm going to take a look and describe the meaning of what we're looking at. Anyway. So if we look at this conclusion here, here's what we can say, right? I'm going to erase this here. Your curve here, this function, let's make sure everything's fine. Your curve f is increasing on the interval from negative 1 up to negative 1/2, union negative 1/2 forever. Okay, so this is where we're finding increasing, because we're looking at these positive slope values for sign analysis. We don't include negative 1/2, And you say, what about where is it decreasing? Well, the derivative is never negative. So what that means is f is never decreasing. You might say, do I have a relative max and relative min? No, if you're standing here, you're not on top of a hill or a valley. Okay, you're not, that's not a hill or a valley at all. So there is no relative max or relative min, because remember, you want to know when you're on top of a hill or a valley, and that's not happening here at all. Okay, there's no hill or valley there you can stand on top of. No local max, no local min. Now, remember what this function is. The reason I'm going to say this is take a look at the function here. This is inverse sine of x over x plus 1. So when I look at Desmos, and y equals functions inverse sine x divided by x plus 1. This is the curve we're talking about. Okay. Over here, by the way, if I try to do something here. Y equals negative 0.5. Or we'll do x. X equals negative 0.5 here. Okay, if I can get in there. Just want to kind of let you guys know. And let's edit this, because I do like to rather have that here, blue and red dotted. Here's my point. See if you can see this point here. Dotted. Okay. This is, you're looking at, ladies and gentlemen, negative 1/2. Remember, the function's not differentiable at negative 1/2. Okay, and this is a strictly increasing slope. Let's see what we did. Yep. But then why are we throwing out quadrant 1? We have to think about, why is quadrant 1 going away? Quadrant 1 is gone. Let's take a look. Two x plus 1 has to be greater than 0. 2x is greater than negative 1. X is greater than negative 1/2. There we go. So this is why your quadrant 1 is gone.